So let's put it back. And we can see that it will count all the way to 63. Hey guys, today we will continue in our series where we go through the courses in FPGA Academy. Today we will look at Lab 4, counters, and last time we finished Lab 3, latches, flip-flops and registers. If you haven't seen it, you can watch it on my YouTube channel. And let's begin with Lab 4, counters, and let's begin with part 1. In part 1 we will try to design this counter. Counter is type of circuit that counts from 0 all the way to some number. So in this case we have 4-bit. That means there are 4 flip-flops, and so it will count all the way to 2 to the number of the flip-flops. In this case 4, so that means 2 to the 4 minus 1. So 2 to the power of 4 is 16, minus 1 is 15. So this counter will count to 15, and it uses T-type flip-flops, which are flip-flops that work as a toggle registers, and I will explain how that works. So we have T-type flip-flops. They look like this, and they use JK flip-flops. And JK flip-flop, so in the previous parts we have created RS flip-flop, but this time we will work with JK flip-flops. And JK flip-flops work as toggle flip-flops. So on the rising edge, if both of the inputs J and K are 0, it will keep the state from the previous one. So if it's 0, it will stay 0. If it's 1, it will stay 1. But if both of them, J and K, are 1, it will change the state to not the previous one. Which means if it's 0, it will change to 1. If it's 1, it will change to 0. And we don't have to consider, in this case, the options when J and K are different, when it's 1 and 0, because TFF connects these two inputs with one wire that is called T input. So both of them will always have the same value. So it's gonna be either this one or this one. That means when T is 1, it will change. When T is 0, it will keep the value. So if T is 1, it will, on the next rising edge, it will change from 0 to 1. On the next rising edge, it will change from 1 to 0. We will also have one more input that will be called clear. And clear will be asynchronous, which means it will work on the clock rising edge as well, and it will clear the circuit. So whatever the value in the circuit is right now in the counter, if it's 8 or whatever number, it will be reset it to 0. So first we have to implement these T-type flip-flops, so let's do that now. I have my quarters project here. So I also imported binary to BCD 6-bit converter we have developed in the previous episodes, and our number to 7-segment display, which takes the BCD number and display it on the hexadecimal 7-segment display. So first we will try to create the T flip-flop entity. So let's create a new VHDL file. I will copy this code. Yeah, I'll copy this whole code. So this is gonna be called T flip-flop, TFF, and it will have 3 inputs: T, clock, and clear. So T, clock, and clear not, because it's negated here, which means it will be reset when clear is 0. And this will be in STD logic. And then we have one output, will be Q, and it's gonna be out and STD logic as well. And then we have to define the behavior. So we will create a process that will change on the clock change. And this process will have one variable called register. and it's gonna be std logic, and we will insert a default value. So this value will be 0. So initial value will be 0. And here we will have if rising edge. So using this function, we can detect the rising edge of the clock. Then and if. So if we have detected rising edge, we will check for clear. So if clear not equals to 0, then, and if it's not, then we will detect else if. We will check for t, and if t is equal to 1, then we will do something, and then we say and if. So if clear not is 0, then we will clear the register. We will set it to 0. If t is 1, we will negate the register, so we will say not register. And then we have to assign the output, so q will be assigned our register. So on the rising edge, if clear not is 0, we reset the value. If t is 1, that means, let's look at here, that means t is set to 1, jk are both 1, and it will negate the previous state. So we will negate the previous state, which is register in our case, and then we save our register to the output, or assign the register to our output. So this is all for our TFF, and now we'll import it to our part 1 as a component, and component here. So like this. So we will need to, I will actually be doing, we are supposed to do 8-bit counter, but I will be doing 6-bit counter that will count up to 63. So we can use our binary to BCD 6-bit converter, and also we can then show it on 2 7-segment displays. So I will need 6 instances of this component. So TFF instance 0, it will be of type TFF port map, and we will need to save our binary number somewhere. So this will store our binary number, but we have to get some wires to get it out of these registers. So this will be called, this will be a signal, it will be called binary number, and it will be std logic vector, and it's gonna be 6 bits, so 5 down to 0. So this one is the first instance. So this one changes the fastest. It changes on every clock. This one changes every other clock, and so on. So this is our instance 0. That's this one. Correct. And that's the least significant bit of the binary number. So port map, we will use switch 1 as enable and switch 0 as clear. So here we have T, that's our enable. So that's switch 1, I think. Yes. And then we have clock, that's gonna be key 0. And then we have clear, which is switch 0. And finally our output, and this is least significant bit, so that's gonna be binary number 0. We create another instance, and this instance will have some input, but this input will be AND between the output of the previous one and the switch. So we have to create a signal T1, It's gonna be std logic, and we can create 5 of these for each of the next T-type flip-flops, like this. We can create a couple more of these as well. So 1, 2, 3, 4, 5. We will create 6-bit counter in this case, so 6 of these. And here we say T1 will be AND between Q and enable. So Q is our binary number 0, and input, which is switch 1. So we can create a couple of these. And we can copy this. This is gonna be bin 1. This. Here one more. So you can see that for example, for the last T-type flip-flop, the T will be AND between this and this and this and this. So between all of the previous outputs and the input. So that's this one, T5. Will be AND between binary number 0, binary number 1, binary number 2, binary number 3, and binary number 4. Yes, so 4 is the last one. And we have to do this for all of them. 4, 3, 2, then here 1 and 2, 1, 2, 3, and then we have to assign them here. So this is gonna be T1, T2, T3, T4, and T5. And also here, this is gonna be T5, binary number 4, 3, 2, and 1. So this seems fine. Okay, so we also have to save this. So I will save this as TFF. And then we have our binary number. So now we have to convert it to BCD. So we will use this component, instance 0. And this component port map. This component takes binary number as input, or binary number as input, and gives us 2 BCD. So let's create 2 signals. Two signals, BCD 0 and BCD 1. They will be assigned to this. So our binary number will be input, and output will be BCD 0 and BCD 1. And then we show them on the 7-segment displays. So here we create instance 1 and instance 0, port map, and we give it our BCD number, and then hex this 7-segment display. So 1 and 1. And I think that's all we have to do. So let's try to compile. Let's see if we have any errors. So the compilation is done. We can try to program our board. And now we can look at the result. So you can see the board here. You can see there are 2 zeros now. So I will set our enable to be 1. I will also set clear to be 1, and then I will press, I will press our clock, and now you can see it incremented by 1. I can keep incrementing. I can try to put our clear to 0, and now on the next rising edge it will be reset to 0. That works. I can try, it doesn't increment. I will set the clear to 1, so now it increments. I will try to put enable to 0, and it doesn't increment now, even though I'm pressing the clock. So let's put it back, and we can see that it will count all the way to 63. So you can see it's counting, and 63, and it will be reset to 0. So that's how this works, and it works correctly. So we can continue, and we have finished part 1. Let's read the implement a 4-bit version of your circuit and use the Quarters RTL viewer to see how the Quarters software synthesized the circuit. So let's look at RTL viewer, how this was synthesized. So we can see we have six our TFF. They look like this. So there are 2 registers, and then our register here. Okay. Let's go back to our top. Go to top level. So this is our converter and our 7-segment display. Okay. Let's look at this. So this is a multiplexer, I think. And then we have our register here. Okay. Let's see the compilation report. So we have used in total 6 registers here. And then logic utilization, we have used 23. Okay. So that's about the RTL viewer. And let's go to part 2. Another way to specify a counter is by using a register and adding 1 to its value. This can be accomplished using the following VHDL statement. So now we will do the same, but using this statement. Compile a 16-bit version. We will also compile just 6-bit. There's no need to do 16. So 23 and 6 registers, and let's try to create another entity. We will call it part 2, and let's copy this code. So part 2, and part 2 will have the same ports. And here we will also have process, and we will have variable. The variable will be called binary. Let's call it binary, like this. And it's gonna be unsigned. And the unsigned, we will be doing 6 bits, so 5 down to 0. So, and the initial value will be all 0. So 1, 2, 3, 4, 5. Let's save it as part 2. And here, if rising edge of the clock, then and if. So if it's rising edge, and we can actually use this code here. So if clear node, which is our switch 0, and then else if switch 1. So if switch 1 is 1, then binary will be binary plus 1. And here binary will be, reset it like this. So that's our binary number. And let's create a signal called binary number. It's gonna be like this, but it's gonna be a std logic vector. So we will assign our binary number to this. And here we will actually need to initiate these components. So let's do that here. Binary to BCD, and we can also copy it from part 1. So this. Then we will have to copy these, but we don't need this std logic. We just need these 3. And yeah, so this should be done. So our TFF is here, or our counter is here, and this counter should count to 63 as well, and then we reset it to 0. So it will basically just overflow, which will reset it to 0. Let's try to compile. We actually have to set part 2 as top level entity, and now we can compile. Unsigned is used but not declared. And we have to use a library. So let's find out what the library is. Unsigned library VHDL. This library. And here we have to also convert to std logic vector. It's gonna be done like this. Let's try to compile now. And clock is not clock, but it's gonna be key 0. So key 0 is our clock. Switch, we have one more error. Expression has 5, expected 6. Okay, there's one more 0 needed. So we will have key 0 as our clock, switch 0 as our clear, and switch 1 as enable. Compilation is done, so let's try to program our board. And you can see again 2 zeros. So let's put our 2 switches to 1. And now let's try to press the key. 1, 2. So it works exactly as previous. Let's try to clear it. It's clear, so works exactly as in the previous one. Counts to 63. So this is done, and let's look at the RTL viewer. We can see it's done slightly differently. We have our binary number here, and then some logic here. So it's implemented different than what we have, what was implemented before in part 1. And let's look at the compilation report. So we can see that even though the RTL viewer was different, we have still used total registers 6, and logic utilization was also 23. So that was part 2. Today we have finished part 1 and part 2. And next time we will look at part 3, where we will use, instead of key as a clock, we will actually use 50 megahertz clock source. And then we will look at part 4 and part 5, where we will do something similar as we have done in part 1 or part 2, which will be shifting DE1 on the 7-segment displays. So if you want to see it, don't forget to subscribe, and I'll see you in the next one. Bye.